Morning, everyone. I hope my slides are visible. Okay, so let's start today's session. Let's wait for a few minutes. Okay. Uh, yeah. Morning, everyone. I'm Karthik Jadhav, currently research scholar in the Department of Water Resources Development and Management, IIT Roorkee. Uh, I welcome you all on the course on irrigation and drainage, and we are currently on week number 8. This course is basically designed by Professor Mailapalli, and he's from EGFE department, IIT Kharagpur, and uh, is part of NPTEL teaching assistant program, and also my duties for PMRF. I've been allotted this course. So yeah, if you have any query related to any uh, course or like any concepts that you have to understand, some question that we have solved and you have doubt in that, so I request you to write down your concern to this email ID. So this is my personal email ID, and just put subject irrigation and drainage engineering in the subject, and try to return email within next 24 hours. And also, I would like to mention here that all the content that I have covered right now till week 7. So I have recorded all that video and uploaded to this YouTube channel. So yeah, I kindly request you to scan this or just click on this link. So you will drive to the YouTube channel and where I uploaded all this content. And also I'm uploading all the lecture materials in this Google Drive format. So kindly access it, and as your exam is coming on, so also it help you to recap everything in a limited time, and also like help you to solve multiple questions. So yeah, these are the overall uh, content that we have covered up till week 7. So yeah, basically we have started with irrigation, what is like how irrigation is relevance, and how like interaction of irrigation water with soil, plant, and atmosphere, right? Sorry, right. Then basically we have talked about various kind of irrigation structures, how we can transfer irrigation water from one place to another place, and different kind of modernization irrigation system like drip irrigation system. Then last week we have talked about performance irrigation system, and one good thing is that we have solved various numerical questions at the end of each week content. So that's a good part in this, and that's also the I'm not covering all the numerical concepts like because we are more focused on and we are focusing on conceptual part, theoretical part, so that are also important as numerical problem. Yeah, though I have few examples at the end of each week, not as much as in like week five because it's also we have a limited time solving session. Yeah, if you have any query or problem, this any of the week, so you can directly write down or you can join this meeting each Saturday like 10 a.m. to p.m. But like this only up to 27th of September, and after that we'll continue regular time that is 26th. Yeah, we are at currently at week number 8, and this we have basically talk about drainage of agricultural land. So yeah, let's go dive into that. So basically, we give overview of this lecture. So in this lecture, basically, we know that there are multiple problems with agricultural land, like there is water conditions, salt affected soil. So all that we need to take care of. So for that we are generally using techniques in it. That basically we have talked, and first we have talked about like water quality aspects, how salt affected soils are harmful, and how waterlogged condition creating critical condition for plant survival. So all that problem leads us to a solution that's drainage, and drainage is the important aspect. So we have summarized this week with in terms of drainage. So and from next week we'll most probably focus on in detail drainage, design, evaluation, and maintenance. Yeah. So before we move on, week 8, so in week 7, basically we have talked about various kind of water lifts, and then basically we have divided them into the indigenous water lift and pumps. And indigenous water lifts are generally divided low head, medium head, and high head. These are the different kind of indigenous water lift, and as of now, they are in use in certain remote areas where there is no electricity. There is unlimited electric, solar, or uh, mechanical power. So that currently are still in use. But now most of things are replaced with pumps, whether it is electrical pump, diesel pump, solar operated pumps. So there are various kind of power supply for pump. And then these pumps are generally divided into the positive displacement pump and variable displacement pump. So positive displacement pump, we know that it discharges the same discharge with respect to head. While in variable displacement condition, as head changes, discharge also changes. And in general, its relationship of discharge and head is inverse kind of relation. And then we have focused on like what is reciprocating pump, what is rotary pump, and its classification. Specifically, we have more focused on variable displacement pump, where we have again specifically focused on centrifugal pump as it is the most common used pump in agriculture, agriculture water management, you can say, irrigation water management. These are the other categories of variable displacement pump. Yeah, this all we have already talked, and yeah, one of the important structure or you can say instrument that in hilly area for water delivery purpose, that is hydraulic ram. So that also we have talked about. And these are the in detail of like what aspects we can differentiate the reciprocating pump and rotating. So these both are actually reciprocating, and these are its classification. So yeah, this is function like the single piston or reciprocating pump. So where every two stroke it leads to discharge of water or any fluid your target. Then variable displacement pump in that basically that all I have already explained. Then we have seen the concept of specific speed in uh, variable displacement pump. So it is just index to the operating characteristics. So it basically provides the relationship between speed, discharge, and head, right? And it is dimensionless number which tells that the speed at which geometrically similar impeller will operate to produce one unit flow and one unit of head. So the equation NS and under Q H by 4. Right. So what is specific speed? So specific speed is basically a geometrically similar impeller would operate to produce one unit of flow Q, one unit of head. Okay. And classification of specific speed. So if specific speed is less than 500, it is a low. If it is between 500 to 100,000, so medium, and if it is greater than 1,000, it is high. Then we have talked about affinity law. So affinity law is the most common relationship between discharge, speed, head, and power. And considering this is the valuable, like very useful in designing of any form. And finally, we have summarized the content with solving by multiple uh, on related concepts. Now we are on week number 8. So week number 8, we have basically started with the problems in agricultural soil, right? In general, we have started with the land degradation, its processes, uh, soil erosion and its type, then water erosion and soil and its control. So why we are learning all this? As our lecture title or this week focus is on agriculture drainage, right? So the major learning of this kind of problems is if your land is degraded, it's suppose salt affected or erosion is happening, right? There's specifically water erosion. So what will be the reason for that? So if erosion is happening, that may be due to the water flowing, so there is no much drainage condition, proper drainage condition in your land. Then if your area is salt affected, so that salt affected again, like that again like fight during like water extraction plant, so it creates osmotic potential, then the osmotic potential ultimately reduce the water extraction. So all these are very critical, right? So considering this, it is just data that it is estimated that worldwide total 5 to 7 million hectare of land vulnerable to agriculture are lost every year through the erosion and degradation. And it's most of the case that fundamental reason is overgrazing and deforestation that generally prone to irrigation. Now in agriculture land also, what we are doing, we are fo- like cultivation of any crop we are doing, we are making the field plain. We are doing tillage operation, that is primary tillage, secondary tillage, tertiary tillage, depending the crop requirement, right? So all that we are making, opened out the field before rain, right? So that cause degradation, that cause erosion, and also like suppose in that you have excess water, and you do not have designed the sufficient drainage condition that leads to water loss. And of course, it like drainage characteristics depends on the soil type. So certain specific soil type leads to waterlogging kind of condition. And these are the just uh, overview of like degradation, like from water erosion, how much land is affected, wind erosion, how much land is affected, and chemical degradation and physical degradation. So you can see in Asian and African condition, or in general, most of the condition, that water erosion is the most influencing factor. Just a second. Uh, Hello. Sorry. Uh, yeah. So I hope I'm audible. So let's continue. So, right. So so water erosion is the uh, more prominent land degradation cause in any region of the world, and due to that, like erosion causes like soil as well as it not allow water to infiltrate. So considering this, if we have proper drainage condition, that will help us. So due to that reason, it is very important. And other aspects, salt affected soil and water quality aspects. So before we go into that, so the fight in weapons against erosion is biological and physical. So biological, like mulching crops to soil, farming methods to terrain, and physical techniques like terrace and dams, controlling gullies, overall watershed management practices, including drainage, right, and certain biological techniques. Erosion control are the most important. Now, these are the general overview, and you can see the land degradation by continent. So, Europe has the highest land degradation, degraded area, followed by Africa, then Asia, then South of America, and then we have North. Then, major type of soil degradation are physical, biological, and chemical. So, we know that physical are just soil erosion by water, then soil erosion by wind, then tillage, soil compaction, reduced water storage capacity. While biological, so loss of soil biodiversity, so let's say overgrazing, Then depletion of soil organic matter, so it overall affecting water absorption capacity, or it also like impacting solute absorption capacity, sorption capacity, and then loss of plant and animal and microbial biomass. In case of chemical degradation, so we have a nutrient depletion, salinization, alkalization, acidification, and toxic contamination. Then we have also briefly talk about types of erosion. So I'm not going into the details. So like that is geological erosion, accelerated erosion, and soil tolerance value. So it is basically value that allow maximum amount of soil that can be lost through erosion in particular year. So then also we have talked about types of erosion. So that is rainy water erosion. So that is different. There are generally four types. So first one is the rain splash erosion, then reel erosion, sheet erosion, and gully erosion. Sorry. Then so yeah, we have also talked about irrigation water quality or in general water quality problems in soil. So it is very important. So if we are doing irrigation water quality water, so it definitely impact crop yield, right? In a long term condition. So characteristic of water that will influence the suitability for irrigation, and poor water quality badly affect the soil structure and overall it impact the crop yield. So there are in general suspended load and dissolved material. So suspended source if it is greater than 50 to 100 micron, so its size is greater than 50 to 100 microns. So it generally called suspended load, and it generally removed by filter. While uh, less than 50 to 1000 micron of the suspended load, it requires flushing. And then we have a dissolved material, so it is the total concentration of ions, usually called salinity. So this is the fundamental aspect, right? Suspended load, we have a two condition in that, like either the suspended load have a size of greater than 50 to 1000 micron. So if size is greater than this, then in that case we require filter kind of material to remove that. While if it is less than 50 to 100, in that case it is less, so we required flushing kind of technique. While dissolved materials, so dissolved materials, so its total concentration of ions usually called salinity, right? And there are two general indicators of water quality. So first is salinity and second is solidity. So salinity is the concentration of soluble salts in water and that generally accumulated over the time. and it creates the osmotic effects. Osmotic effects is generally uh, it generally develop a condition that fight with the plant water. Like if plant want to acquire water or uptake the water from soil water, so in that case, what happens if there is a higher salt present in your soil, so that impacts overall. It's just fighting with that water, and it won't allow plant to take water. Then we have a sodicity. So sodicity refers to the concentration of sodium relative to the other cations like calcium and magnesium in irrigation water. And generally US salinity diagram for classification of irrigation we are using for this kind of situation or classification of this kind of condition. And finally we have talked about iron toxicity and other water quality parameter. But main thing is salinity and sodicity, as this is the most common problem or fundamental problem in most of the arid region due to the higher evaporation. And then we have also talked about effect of water quality in micro irrigation system emitter clogging. Obviously, if you have a poor water quality, higher suspended load, like if it is greater than 500,000 microns, so definitely uh, it will require filtration system. Otherwise, what will happen? It will cause clogging in drip irrigation system or micro sprinkler irrigation system. Because you know that this kind of system have a very small diameter at the outlet, and that overall impacting. And major chemical constituents in water associated clogging problems that you have also talked, and what kind of management practices that required to treat poor water quality. Then we have also talked about soil acidity, nature of man-made cause of soil acidity, then rules of soil acidity, and ameliorating of soil acidity. So soil acidity basically refers to the process of excess hydrogen ions and aluminum ions in soil solution that leads to the low soil pH, that is generally below 7, and highly acidic soils like pH less than, if pH is less than 5.5, it can significantly impact the plant growth, microbial activity, and nutrient availability. Because you know that acidic condition have a higher presence of hydrogen ions and aluminum ions. So this overall, like what happened when this become higher in soil, so it fights with overall water and like other nutrients, and it absorbs like on the, if soil is acidic, so it attracts towards acidic soil, and if we are adding something, so that not reach out to the plant. So it's generally fighting with the plant, and it impacts its growth, right? So pH scale and soil acidity. So generally it's classified in a four scale. So if you have a natural soil or neutral soil, its pH is around 6.5 to 7.5. Then slightly acidic soil. So in that case, we have pH is around 5.5 to 6.5. Then moderately acidic soil. So in that case, 5.5 to 4.5 to 5.5. Strongly acidic soil if pH is less than. Now, how it's impacting soil? It's affecting nutrient cycling by reducing the availability of essential nutrients like phosphate, calcium, and magnesium, right? So you can see this, as I already highlighted, that increase in the solubility of toxic metals such as aluminum and manganese. So it also harmful for the plant. Generally fights with other essential nutrients. The cause of soil acidity is, so there are two causes, so either it is a natural cause or man-made cause. So natural cause, like Rainfall and leaching. So higher precipitation leaches the basic cations like calcium, magnesium, potassium, sodium. So it's replacing them with the acidic ions like H plus and aluminium 3. So other is weathering of minerals. So breakdown of soil minerals that releases the acidic cations like hydrogen, then aluminium, and organic matter decomposition. So produce organic acids that contribute to soil acidity and microbial activity. So during nitrification process, so there is conversion of ammonia to nitrate, right? And this process generally release the hydrogen ions, so it ultimately also increasing acidity. So, so naturally there are four cause or four second, uh, there are four causes that generally lead to increasing the soil acidity. So either it is from a rainfall or a leaching, rainfall leaching, either it is a weathering of minerals, so acidic minerals, those acidic cation specifically, then organic matter decomposition. So whenever organic matter get decomposed, it have a it or it produce the organic acids, right? And that contribute to the soil acidity. And finally, microbial activity. So nitrification. In case of nitrification, there is a conversion of ammonia to nitrate. So you can see this hydrogen ions get released, and that ultimately increasing in hydrogen ions that causing a condition like acidity. Then man-made cause, so there is a excessive use of ammonium-based fertilizers. So you can see that ammonium generally, if you are applying ammonia to the soil, so if plant want to use so, that ammonia, so ammonia must convert it into the nitrate. And you know that once it gets converted into the nitrate, so it always releases the H plus ion, and that increasing in H plus ion that ultimately causes the acidic condition. Then also there are certain places we have acidic rain. So during initial rain, like first week of monsoon, or whenever monsoon gets started, at that time generally we found that acidic rain of condition due to presence of sulfur dioxide, NOx kind of uh, gases in air. Then intensive agriculture, so repeated cropping and heavy irrigation accelerate the nutrient depletion and acidification, right? Because intensive agriculture applies lots of fertilizers, so that fertilizer ultimately leaching down toward the soil, and that leaching down ultimately there are complex processes and ultimately increasing of certain cations and aluminum ions, and that leads to soil acidification and deforestation also leads to it. So generally in deforestation, if we are removing the vegetation, so we are generally reducing the organic matter buffering and that exposing soil to acidifying. Yeah, so always remember that either by adding some we are doing certain uh, problems like acidification, right? Or other cases just doing intensive cultivation or farming, and for that we are using excessive fertilizers, certain kind of fertilizers, and also there are natural causes like by just natural activity that is happening in nature. So general basic difference in natural causes and man-made causes. So it is naturally happening, and that is required for like a cycle of that overall life cycle. While in man-made cause, what is happening? Generally, man-made cause that happens due to the we are excessively applying, or we are like accelerating this natural causes by adding certain chemicals into the atmosphere or soil, or just doing deforestation, overgrazing. So this kind of condition also cause reduction in organic matter in that soil, and this generally reduce the buffering capacity of soil acidifying effects. And we have also gone in detail. So this we have not talked in detail, but I hope that, or like I have found that this may be useful for you to overall understand of the water chemistry or soil water chemistry. So then we have also we can link this with the pools of soil acidity. So soil acidity exists of three interconnected pools. So active acidity, exchangeable acidity, and residual acidity. So active acidity like solution acidity. So it represents the H plus ions in the soil solution and determines the pH of the soil. Then it basically influences the plant growth and microbial activity. Then we have a exchangeable acidity, so composed mainly of aluminium and hydrogen ions held on a soil colloid, and that can be easily displaced into the soil solution, affecting plant roots. And finally, we have a residual acidity. So it is the largest pool found in the soil minerals and organic matter, and released slowly over time and affects the long-term soil acidification. And now comes if there is a problem with soil acidity. Yeah, so let me quickly summarize this. So pool of soil acidity, generally we have active acidity, exchangeable acidity, and residual. So active acidity means it basically or like represent the H plus ion in the soil solution, and it is an active condition, and it immediate impact the plant growth or microbial. So it is active, right? And exchangeable acidity, so it composed mainly of aluminium and H plus ions held on soil colloids. And this can be easily displaced into the soil solution, affecting the plant roots. And third one is a residual, and it is the largest, right? And this slowly released all these cations into the soil, and it ultimately leads to the soil acidification. So generally, lime application is a primarily neutralize exchangeable and active acidity, right? So generally, to reduce the soil acidity, we are applying the lime, and long-term management is required to address the residual acidity. So for like this first two one, active and exchangeable, we can reduce it by applying lime. But for this, we require certain measurements. So methods for reducing the soil acidity. So lime application is the most common method. So lime is basically calcium carbonate, right? CaCO3. Then we can also apply certain like dolomitic lime, then quick lime. So there is type of lime. So basically it contains the calcium. So what lime does? So lime neutralizes the hydrogen and aluminum, raising soil pH and improving the nutrient availability. Then use of gypsum. So lime and gypsum, the gypsum like again CaSO4 into 2H2O does not increase the soil pH but reduce the aluminum toxicity and improves the soil structure and water infiltration. Right. So if your aim is to just reduce the aluminum toxicity in the plant, because you know that even in uh, trace amount presence of aluminium in soil, that badly impacting the plant growth. So if your soil have a higher aluminium content in your soil, in that condition, you must use gypsum, right? So gypsum helps to reduce the aluminum toxicity and also improve soil structure and water infiltration. But lime in general is the most common applied if you want to reduce. like if you want to increase the soil. Then organic amendments. So as we know that organic amendments like compost, biochar, and manure increase the soil buffering capacity. Right, buffering capacity means like resistance to change in soil pH, and organic matter enhance the cation exchange capacity. So it ultimately is not like that. It not won't allow easily to attach the hydrogen and aluminum ions. So it makes certain balances. So these first three are basically about adding something, amendments, or applying certain chemicals. Now, if we focus on certain management aspects, so these three are more about management aspects. So, proper fertilizer management, so reduce ammonium-based fertilizer, use nitrate-based fertilizer to minimize acidification, then crop rotation, cover crop. So, all this like leguminous plants help to fix nitrogen naturally, reducing fertilizer needs, and deep-rooted crops improve the soil aeration and nutrient cycling, and buffer strips and afforestation so it protects soil from acid rain and erosion, and it generally maintains the long-term pH stability. Then we have a concept related to alkalinity and salinity. So in that also we have talked about what is difference between salinity and alkalinity. So salinity generally is a critical factor affecting crop productivity, soil fertility, and water availability. You can see that any problem in the soil, like either it is related to acidity, sodicity, salinity, alkalinity, so all this impacting entire, it's not only impacting soil, right? It impacting that growing plant in that soil fertility as well as water availability, right? Because fertility, like fertilizer availability and water availability, is the fundamental requirement of any plant. And if you have a condition like salinity and acidity, uh, uh, salinity, alkalinity, then you have suppose sodicity. So all this generally reduce the fertilizer and water availability, and that ultimately impacting the crop product. So this problem arises due to the natural processes and anthropogenic activities, as already highlighted in for soil acidity. So in natural growth of alkalinity and salinities, like weathering of parent rock containing salts and high evaporation in arid and semi-arid region, that leaves the soil behind if there is a high capillary rise, or if if we are irrigating with the salt affected irrigation water. And that anthropogenic causes are uh, excessive irrigation with poor drainage, so that leading to waterlogging and salt accumulation, and use of saline groundwater for irrigation, and application of chemical fertilizer and industrial irrigation. So yeah, nowadays there is also like increasing in use of treated wastewater for irrigation purpose, so that also contain lots of chemical and waste, so that also may lead to the salinity and alkalinity kind of. Yeah, so first one that we have talked about is exchangeable sodium percentage, so that is ESP. So ESP quantifies the production of sodium ions occupying cation exchange sites of soil relative to the total cation exchange capacity. It is calculated using formula, and ESP value above 15% indicate the sodic soil. It means more sodium content, and which are associated with the poor soil structure, low permeability, and IDE. And sodic soil leads to the dispersion of soil particles, making them prone to waterlogging and erosion. Right. So why we are learning this? So if you have a high sodicity, in your soil, so that leads to poor soil structure, low permeability, high pH, and ultimately it reduces the drainage. So in this high sodicity soil, we require drainage condition, and ultimately come on that topic. So these are the formula like exchangeable sodium, your cation exchange capacity. So this is formula. And then we have a sodium adsorption ratio. So it is generally a measure of sodium hazards in soil and irrigation water, and it assesses the balance between sodium, calcium, magnesium, and other cations. Yeah, generally it's between sodium, calcium, and magnesium, and its value are given here. So these are the most common classification of salt affected soil. So generally these are the like most common. If you have saline soil, its pH is greater than generally 4 decimels per meter, and saline sodic soil again for that also we have 4 decimels per meter, and sodic soil, so there is black alkali soil or alkaline soil, it have a less than 4 decimels per meter. And sodium percentage, so in sodic soil we have a higher sodium content, so it have a greater than 15, but in case of saline soil it is a less than 15. And these are the major ions contribution in this kind of soil, right? Please go through it, and these are the reclamation and management practices for salt affected soil. So, saline soil management, so leaching of soil below the root zone using good quality water. So, it is basically drainage. Then, improving drainage to prevent salt accumulation. And if you have a sodic soil, so sodic soil generally you need to sodic soil. It means you have a higher sodium in your soil. So, just apply gypsum to replace the sodium. So gypsum is CaSO4 again. So lime, gypsum, then what we have seen for acidic soil. So that is again, yeah, gypsum. So for acidity as well as uh, salt affected soil, right? Saline soil. So we are generally not saline soil. So saline soil it is only we are generally using leaching of salts and proper drainage condition. But if you have a higher sodium in your soil, right, or any other cation, so that ultimately like aluminum or H plus, this leads to soil acidity, and this if you have higher sodium content, that leads to soil like sodic soil, right? So it means if you have a higher salt sodium content, so it required application of gypsum, adding organic matter to improve soil structure and buffering capacity, and doing a deep clay operation and process of drainage condition. And if you have a saline sodic soil management, so in that it is saline also and sodic also. Saline means higher salt, sodic means higher sodium. Sodium means it is cation, so it required gypsum again, right? While for saline soil, we required leaching of that salt. So basically, generally in saline sodic soil, we are what we are doing first. We are adding gypsum. So gypsum generally reduce the sodium content, and then we are applying. We are creating drainage kind of condition to leaching out of this salts. And then these are again problems related to the submerged soil and type, characteristic of submerged soil, and importance of submerged soil. So submerged soil generally refers to the soils that covered with the water for prolonged periods, resulting in a unique chemical, physical, and biological. So always, if you have a certain condition like waterlogging, if you are applying irrigation, if you are doing certain recharge. So you must remember that if you are doing certain events, or whether it is happening naturally or man-made through anthropogenic activity, so all this causes unique physical, chemical, and biological properties of that particular soil or like surrounding condition. And this soil are significantly in wetlands, paddy soil, flood-prone areas. So it plays crucial role in agriculture and environmental sustainability. So there are three types of submerged soils. So one is a permanent submerged soil, seasonally submerged soil, and intermittently submerged soils. Permanently found in wetlands, lake, estuaries, so it remain underwater throughout the year. And seasonal, so found in a floodplains and paddy fields, where submergence occurs specific reason due to rainfall or excess irrigation. And then intermittently submerged soil, so this soil experience the periodic drying and wetting cycle affecting the nutrient dynamics and microbial. And then we have focused on chemical properties. So they're related to the irrigation water. So these are the all condition that so I'm not going into details for submerged soil, right? So chemical properties, then biological property, physical property, and this all condition at like for at least agricultural land we required access or proper drainage condition to remove excess water in case of seasonal flood or like excess water irrigation condition. Then we have talked about water movement within soil. So as like understanding of drainage will come only if you have proper understanding of uh, how water infiltration to the soil, then what are the parameters like soil water content, then soil water like soil water head or metric potential, how it relates at different soil moisture content, so soil moisture characteristic curve, then how we can measure soil hydraulic conductivity in the field, as all these parameters are very important for the design of drainage system. That purpose, we have started with the water movement within soil, so either it is saturated flow, unsaturated flow, and vapor movement. These are the difference between them, and I'm not going into detail. Then we have talked about different soil moisture constant, soil field capacity, wilting point, and let's say available water. All this we have already talked, and then not all going into detail as we are going to cover similar question for that, and we are running out of time. Uh, this is again different coefficient, and these are the fixed law. So fixed law generally it's diffusion help us to identify diffusion coefficient. And then finally we have discuss about drainage agriculture. Right? So major problem we have in right now is either it is a too much of salt in our soil or there is a poor drainage condition, and that all impacting soil structure, uh, soil structure overall impacting water availability, then plant uptake, so it impacting overall crop productivity. So agriculture drainage is just removal of excess water or salt from the root zone to maintain the suitable condition for plant growth. So excess water can come from rainfall, irrigation, or groundwater rising. And now, what are the need for drainage? So drainage help us to prevent the water logging, and improves the root aeration. It controls the soil salinity and alkalinity, so by flushing the soils and improve timely field operation. We can carry out if not a waterlogged condition in your field, so of course you can easily do certain farm operation like plowing, sowing, and harvesting, and enhance the crop yield and quality. And now comes to like what kind of drainage system we have. So in general, so there are two type of drainage systems. So first one is a surface drainage, and second one is a subsurface drainage. So surface drainage, so it removes the excess water from land surface using shallow ditches and field channels, right? So suppose you have your farmland like uh, suppose you have farmland like this, then you need to remove excess water from this. So you create certain channels. Like suppose this is your main channel, then your farm here. So for this, you just divert this water from here to here. If it's a waterlogged area, suppose again this is the waterlogged area, so connect this waterlogged with this main channel. So what happened due to this gradient, created a gradient, this water just moved from here to here and ultimately will correct this at the end. And subsurface drainage, so remove water below the surface by installing tile drain, perforated pipes, mold drains, or tube drains. And it is generally best for waterlogged and saline soil. Then what we need to consider during design of the drainage system. So generally first come into the picture is the drainage coefficient. So it is generally depth of water that we must remove per day. Right, so the depth of water in that must be removed in 1 day. And all this depends on the soil type, topography, rainfall, crop sensitivity, water table depth, and so on, right? And benefit of agriculture drainage. So yeah, of course, what are these needs? Of course, here also. And but there are certain challenges. So challenges like there is a high installation cost specifically for subsurface drainage. Then we need to do certain maintenance practices like sill deposition and clogging of drainage pipe and disposal of saline drainage water. So yeah, if we are removing water from here and we take certain sediments, so there are silting of this channel. So once water flow from this to this, again silt carried out if flow will continue. Also impact this capacity. So you need to remove this all, and if you are doing drainage with the pipe, so in pipe also there is a logging kind of condition, and also there is a disposal of saline drainage water. So it is environmental concern. So if you are collecting from here, right, from your farm, but where you are disposing, so again this thing is going to meet the certain river or ocean or nature water bodies. So again, it harming our natural environment. Yes, that also you must have considered. That's why best practices nowadays, like people are talking about, is sustainable development. So you need to use minimum of chemicals, minimum requirement for your daily needs. So like because you not harm other nature for your own benefit. That's always like uh, trade-off between different aspects of this. So, but this is the right now the reality. It is, and then overall, so agriculture drainage systems we are using to remove the excess water or salts, and two main types in summary. Either it is a surface or subsurface. So surface also called a ditch type or subsurface pipe or tile drain. And a key role of this kind of drainage activities control water logging, manage salinity, and improve aeration. And it's basically essential in heavy soils and irrigated cropping systems. Okay, so now we are on question and answer session. So, okay, let's take uh, 5 minute break here. Then we'll be continue this question and answer session. So, yeah, I've designed certain questions according to these concepts. So, yeah, just then we'll be again continue this. So, question number one, what does the SAR stand for? Irrigation water quality. So, know that SAR stands for sodium absorption. So generally, sodium absorption ratio, it is crucial parameter in at assessing the quality of irrigation water. It measures the relative amount of sodium compared to calcium and magnesium in. It is higher sodium absorption ratio value indicates a higher concentration of sodium in. Now, if sodium is higher, so there is a poor soil dispersion. So sodium ions can disperse the soil particle, leading to breakdown of soil structure. So if sodium is higher, it means poor soil structure. So you might observe this in a like coastal region. So due to higher salinity, what is happening there? There is a creation of cracks, right? Then reduce infiltration. Again, yeah, disperse soil particle, clog pores and reducing water infiltration and increasing the runoff. Then alkali hazard, nutrient imbalance, and reduce crop yields. So of course, these are the other aspects. So first one, remember, is that there is a dispersion of the soil, right? Dispersion of soil particles. So it affect the soil structure, then reduced infiltration due to clogs and alkali hazards. So high SAR can lead to development of alkaline soil with high pH. Correct answer is Darcy's law case at stands for. Know that Darcy's law is defined as Q is equal to, so it is basically discharge is directly proportional to uh, hydraulic conductivity, or just you can say hydraulic gradient times A, or you can say Darcy's just velocity proportional to hydraulic gradient. Then you will introduce uh, proportionality constant, that is K times I. So this is your velocity component, and if you multiply this by area, then you will get the discharge. So here K is basically hydraulic saturated hydraulic conductivity, right? Because Darcy's law is generally valid for saturated porous media, and that leads to the saturated hydraulic. Correct answer is option B. Saturated flow occurs, so it is downward, horizontal, upward, or all of the above. So you know that saturated flow, so downward, water moves vertically due to gravity. You can see if it is like it's moving vertically, seen after rainfall, irrigation, when soil is saturated, then horizontal flow, of course, like base flow. You can say once water will reach here, it will also moving horizontally as a base flow and ultimately meeting the surface water, and upward flow, yeah, due to capillary rise and higher water level, right? In this case, water will also move at capillary rise level. And the correct answer for this is all of the above. Which portion of soil water is available to plants? We know that, so there are different kind of conditions. So it is saturation, field capacity, and fermentation point. Plant available water is a field capacity and permanent building. Correct answer is yeah, option C. And why it is like that? So we know that field capacity is basically maximum water amount that can be held by soil against the gravity, and permanent wilting point is the moisture level at which plants can go no longer for water extraction. That cause ultimately wilting condition. So water available in between is called the soil water available to plants. So option C is total suspended solids in irrigation water is measured by. You know that TSS is generally measured by gravimetric method. So correct answer is option A. So once you have collected water, either it is you are from experimental side, real field side. So what you are doing? So you are just filtering out that this water with this filtration, vacuum-based filtration system, and you will have this now like evaporate this as it have a water. So either you put it in the oven at certain temperature based on like content here and water content obviously. Then you just use this weights to get the total suspended solid and dissolved solid. Question number 6: which soil has the highest wilting coefficient? So you can see this like soil water content and field capacity and permanent wilting point, right? So highest wilting coefficient means, so first there are different kind of soil. We know that whether it is a clay. So clay soil have a very low size as compared to seeds and loam. And you can see for like sandy soil, there is a low water availability due to higher pore space, or you can say due to higher larger particle size that quickly drain out condition is happen there if even water is available. So wilting point and field capacity or total available water for sandy soil is too less. So our first option is allowed. Then we have a silty loam. So silty loam you can see like it is around like highest water, highest field capacity, as well as it have a low permanent building point. So this total difference is ultimately plant available water. So it is higher in case of silty loam. Then loam. So loam again, we have a same, but it lies here, right? But in case of clay, so as we know that clay have a very a small particle, and it have a highest wilting coefficient because it contains the water, but it holds too tightly, so it is not available to plant. The answer is option D. Right, so clay consists of soil particles less than 0.02 mm and feels smooth and sticky when wet and has a highest water holding capacity due to its small. Question number 7. The range of metric potential in field capacity is. So, you know that during field capacity, so you can see this metric potential values. So, in field capacity is it is in general between uh, minus 10 to 30 kilopascal. It is in general like minus 110 to minus one third R, and this generally you can see 0.1 to minus 0.33. Now 1 bar is equal to, you know that, 10 to the power 5 Pascal, and then this if you convert into kilopascal, so it is 100 kilo, right? Hope you got it. And now you can see just divided this by 100. Sorry, just multiply by this with 100. So this will come is around minus 10 to 20. Question number 8. The difference between field capacity and hygroscopic coefficient is termed as. So field capacity and hygroscopic water is generally called available water too. So option, oh sorry, uh, this difference between field capacity and hygroscopic coefficient. Available water is basically water held between field capacity and permanent melting point, not hygroscopic coefficient. Then capillary water, so water held in soil pores by surface tension that is available to plant. So whatever water stored in between field capacity and hygroscopic coefficient is termed as capillary water. Then match type of condition question. So Okay, so let's continue our session. Yeah, so electrical conductivity, we know that is a measure of salinity level in water. So measures the water salinity level, then sodium adsorption ratio, so it indicates risk of sodium affecting the soil structure. So yeah, it is matching this. Then we have a pH, so it is basically ideally between 6.5 to 0.4, right, for irrigation water. And total dissolved solid, so dissolved solid provides a measure of overall salinity. So TDS water is generally overall salinity, so it is matched option A. And residual sodium carbonate, so high residual sodium carbonate value indicates risk related to sodicity and alkalinity. And boron and other toxic elements is like acceptable concentration, very point different. Salt of that, so it's easy one, I think. So this overall irrigation with contaminated water and surface water and wastewater. So how it impacting overall nutrient balance, and also it might help to take up this kind of essential nutrients, but also there is a problem related to the leaching down of this kind of emerging contaminants or heavy metal. Yeah, so this again the match type of question. So C1, C2, C3, C4 is the type of or class of water you generally use to classify the low salinity water. So C1 is the low salinity water, and generally electric conductivity in this kind of water is less than 250 microsiemens per centimeter and suitable for almost all crops in a soil. So C1 it's can cause a significant can be used for irrigation with most crop, but some salt sensitive crops may. I think sorry. Yeah. So C1 is basically water have a low salinity and suitable for almost all crop, and its have a salinity is less than 250 microsiemens per centimeter. And C2, it is a medium salinity water, and EC is between 250 to 750. And water can be used for irrigation for most crop, but salt sensitive crops that are not suitable. Then C3, like high salinity water. So in that case, like significantly salinity problem and suitable for salt tolerant crop with good management practices. And C4, so it is greater than 2250 microsiemens per meter, and it is unsuitable for most crop in soil. So C3 is like high salinity water, and water can like we can use, but there are certain management practices are required. And C4 is generally unsuitable for irrigation. It is called very high salinity. Yeah, this is just again type of sodium adsorption ratio and classes. So these are the important aspects, and to classify sodium adsorption ratio also, like again like C1, C2, C3, C4. We have S1, S2, S3, S4. So S1 is low sodium hazard, then medium sodium hazard, and S3 is a high sodium hazard, and S4 is a very high. So low, medium, high, and very high. And low is about less than 10. If the value of sodium adsorption ratio is less than 10, and it's called a low sodium hazard. That if you have a medium sodium hazard, if it is in between 10 to 18, and high sodium hazards if it is in between 18 to 26, and if it is greater than 26, so it's called very high sodium hazards, and it is unsatisfactory for most of the greater zeta potential. So zeta potential is basically made up of electrical charge on surface of particles in suspension, and higher zeta potential creates stronger repulsive force between particles and preventing them from aggregating and thus increasing the stability and suspension. So higher zeta potential, it basically means higher electrical charge on surface particles in suspension. So this the higher charge around this particle, so it ultimately cause the attract different kind of positive and negative ions, and it ultimately increase the stability. So correct answer is option C, that it is a more stable suspension and particles tends to repel each other. So A and B are acidity caused by hydrogen and aluminum ions in exchangeable sodium sites or introduced to. So yeah, like hydrogen and aluminum ion generally causing the acidity related to the residual acidity, right? Correct answer is option. Oh, sorry, it is at in exchangeable sites. So if it is happening in exchangeable sites, then it's called exchangeable acidity, right? Because residual is associated with the non-exchangeable hydrogen and aluminum ions, tightly bound to soil. Next question. So Darcy's law is applicable to which type of fluid? So we know that it is for saturated porous media, and flow condition that are more suitable for Darcy's law is laminar flow. And this Reynolds number is most probably less than 10, and usually it is like acceptable. Acceptable is less than 10, but usually like it must be less than 1. So these are different characteristics of laminar flow, turbulent flow, mixed flow, and suspended flow. Then, which of the following parameters does Darcy's law consider as a constant for given soil? Yeah, we know that Darcy's flux is defined by K times I. I is basically hydraulic gradient. You can also write it as a delta H by L. There you can say length. So here just K is the constant and also called the permeability. Yeah, so these are the just physical, chemical, and biological contributors to clogging in micro irrigation system. So it's just for your information. Please go through this. This is very important aspects to get aware about all kind of physical, biological, and chemical participants in clogging of micro irrigation system. Then, what are the characteristics of saline soil? So we know that these are the just classification of saline, saline sodic, and sodic soil. So saline soil, we know that in that case, extend sodium electrical conductivity, like overall salt amount is higher, right? Uh, and that also known as the white alkali soil. But in case of saline sodic soil and sodic soil, so sodic soil contains the sodium content. So in that case, exchangeable sodium percentage is higher. And if saline comes, so EC is higher. EC is generally representing overall salt, or you can say overall saline. So, what are the characteristics of saline soil? So, saline soil, what we need to identify, it represents the overall salinity of the soil. Overall salinity is electrical conductivity must be greater than 4 decimal meter. So, this case is given greater than 4, then again greater than 4, again greater than 4. Now we come to the picture that Let's check about exchangeable sodium percentage. So yeah, of course, it is less than 15.4 saline soil. So it is given greater than greater. So correct answer is option A. Base saturation is generally sum of base cations divided by cation exchange capacity. So it is just a proportion of cation exchange occupied by non-acidic cations like calcium, magnesium, potassium, and sodium. Next question. Sodium adsorption ratio gives information on comparative concentration of sodium, calcium, and magnesium. Yeah, it is true, right? Because it's a key indicator used in soil science to determine the relative proportion of sodium to calcium and magnesium, and it provides crucial information about potential for soil dispersion and structural degradation. Based on soil adsorption ratio, we can decide for soil dispersion, structural degradation due to excessive. And next question, what happens to redox potential when soil is submerged? We know that when soil is submerged, its redox potential changes due to depletion of oxygen and progression of microbial reduction reaction. And redox potential represents the electron availability in the soil and influence nutrient availability, microbial activity, and chemical transformation. So we know that under submerged condition, redox potential generally due to depletion in the oxygen. So there is a reduction in redox potential rather than increase. So first is incorrect. So decrease subsequently. Yeah. So when soil is submerged, oxygen is gradually depleted and by microbial respiration leading to anaerobic conditions. What is happening? Like there is a submerged soil, right? So water is there, right? This then what happened? Like if it is a submerged soil, so redox potential generally decreases. Why? Because there is a limited air present in this or oxygen present in this soil, submerged soil, and that also like continuously used by microbes that present in soil for their survival. Due to that, there is again reduction in oxygen. So uh, that reduction in oxygen that reduce the redox potential. Correct answer is option. Question number 18. Why soil buffering capacity is important? State the incorrect state. We know that uh, resisting just buffering capacity is like can making a lime recommendation for acidic soil, and it can potentially use for making recommendation for decreasing pH for soils. And if valuable soil property for estimating pH changes for some nitrogen reaction in soil such as urea hydrolysis, nitrification, and soil retention. So only active acidity should be considered while liming. Right. Correct answer is this first three, and incorrect is option D. Because this all reasons are I'm not going into this chemistry as like it's not part of this, but I've just put this question for you and just go through this description. If you have any query, let me know. Next question, the leaching fraction is defined as, so leaching fraction is, we know that Irrigation water often contains salts, and when water infiltrates soil, plant use a part of it and rest moves down. And salt, if salts are not removed, so it accumulates over time in root zone and ultimately harming the crops by affecting the soil structure. And to prevent this, there is introduce of leaching fraction. So leaching fraction is just ratio of applied depth, or as you can say, seepage depth, or just depth of percolating water through root zone divided by applied depth, irrigation plus precipitation. So it is just ratio of irrigation water depth to seepage depth. No, it is seepage depth to applied depth, right? So this the overall salt balance concept in drainage condition. Yeah, again, go through this. We have already covered, right? All concepts. So not going in detail due to there is a limited time and also I'm facing an issue. Now, next question: main objective of agriculture drainage is to. So we know that increase control the excess water in roots. The answer is option. Again, drainage is the most essential for which type of soil. You know that heavy clay soil, rice wheat system, it have a low permeability and that prone to clogging, and this also causes secondary salinization. So correct answer is option. Okay, so numerical type of question. So let's do that also. So an irrigation water sample has following concentration of soluble ions in milliequivalent per liter. So these are the concentrations. We need to calculate sodium adsorption ratio. You know that sodium adsorption ratio is given by sodium concentration in milliequivalent per liter divided by under root calcium plus magnesium divided by sodium divided by calcium plus magnesium by 2. So all these are given in milliequivalent per liter. Yeah. So always remember that you need to convert, if it is given in ppm, you need to first convert it to milliequivalent per liter. So let's just put first of all this under root calcium plus magnesium by 2. So it will be around 3. Then 12 is given for sodium. So overall answer is 6.93. Sodium adsorption ratio is 6.93. If you remember that for classification of sodium adsorption ratio will be S1, S2, S3, and S4. S1 is if it is less than 10, so it is low sodium adsorption ratio. 10 to 15 and 18 to 26. So it is low, medium, high, and very high. Irrigation water has electric conductivity of is around 1.5 decimeters per meter and leaching fraction is 0.25. Find the electrical conductivity of drainage. We know that there is simple relationship between leaching fraction. So leaching fraction is defined as EC of drainage water divided by so irrigation water divided by EC of drainage water. So always remember that drainage sorry bleaching fraction is like 0 to 1. You can, if we are presenting in percentage, it is 0 to 100, and it is defined as EC of irrigation water divided by irrigation of drainage water. EC of we need to identify EC of drainage water. So just instead of irrigation water divided by leaching fraction, you'll get irrigation drainage water. Now, if applied irrigation depth is 200 mm, average salinity is 2.5 gram per liter, and leaching fraction is 0.4. So concentration of draining water is required. So again, leaching fraction we know that is equal to C in divided by C out. So you can just say that EC of irrigation water, EC of draining water. Here they measure concentration, so you can still use this formula. We need to identify C out. C out means concentration of draining water. It is just concentration in irrigation water divided by leaching fraction. So it is around 6.5 gram per liter. So draining out irrigation water has concentration of 6.25 gram. Okay, so yeah, this lecture is like completed now. So yeah, if you have any queries, we can take that. Anyone? Uh, okay, so I think if you do not have any queries, so let's quickly summarize this session. So yeah, in this we will basically talk about drainage of agricultural land. So, but before that drainage aspect, we have first talked about what are the different water quality problems, salt problem in soil, also what will happen in waterlogged conditions. So all that cause major problems. So it comes under degradation of lands, and then we have talked about water quality aspects. So that is sodicity, acidity, alkalinity, all that we have defined, and how we can use like sodium hydrogen ratio, acceptable sodium percentage, define sodicity and alkalinity for actionable sodium percentage, you can say. And then finally, we have started about talking about irrigation, agricultural drainage. Agricultural drainage, yeah, of course, we have just started this, and in the next we have probably we have seen various design aspects of grids and maintenance aspects. Yeah, then we have also solved multiple choice questions based on the concept we have learned and certain numerical questions. Yeah, thus with this, like we have ended this session. So, okay, yeah, if you do not have any questions, so I'm ending this session. Yeah, I would like to request you like watch out all the previous content, uploaded video content here by scanning this QR code or just simply use this YouTube link. Also, you can access lecture material here. I will upload this PDF and this format for today's session, and also all the previous slides are also there. Yeah, with this, so thank you so much for joining today's session, and yeah, I hope you are learning, enjoying this session. Yeah, so thank you so much again.